So as we mentioned when we were introducing vectors, one way that we can report what a vector is tell what its magnitude is and in which direction the vector points. There's a second way that we can report a vector, and that's by telling someone what the components of the vector are. So let's start by being clear about what we mean when we talk about the components of a vector. So for starters, the component of a vector is the projection of that vector along a coordinate axis. So what does that mean? Well, notice that here we've got two axes, right? We've got the x-axis running left and right, we've got the y-axis running up and down. So what the x component of vector c is going to tell us is it's going to tell us how much vector c points in the x direction. So in terms of having said that the x direction represents left and right, it's going to say how much does vector c point left or right. The y component tells us how much the vector points in the y direction. So again, y here, given our choice of coordinate system, the y direction is telling you about stuff going up and down. And so the y component is going to tell you how much your vector points either up or down. The easiest vectors to start in terms of breaking up into their components are vectors that lie along a coordinate axis. So here vector A lies along the x-axis, vector B lies along the y. And so what makes this situation a little bit easier is that if you have a vector that lies along a coordinate axis, what that means is all of its magnitude has to be projected along that axis. So in terms of thinking about three things to figure out the components for a vector that lies along a coordinate axis, the first thing we're going to do is figure out, well, which component has to be 0. Then we know that the absolute value of the other component has to be the magnitude of the vector. So all that magnitude has to go in the non-zero component. And then the last thing we need to do is figure out what the sign of that non-zero component is. So if we think about the two vectors that we've got here as examples, well, vector A lies along the x-axis, which means its y component has to be 0. This is another way of saying that lying along the x-axis means that vector A doesn't point up or down at all. It doesn't point in the y direction at all. The x component then is going to get all 12 meters. So we know the magnitude of vector A is 12 meters. All that has to go into the x component. And then what's left is, well, what's the sign of that x component? And since vector A points in the positive x direction, I need a positive sign. Vector B, on the other hand, lies along the y-axis, which means it doesn't point left or right. So its x component has to be 0. The magnitude of vector B is 15 meters, so all 15 meters has to go into the y component. And in terms of sign, if positive y points up, then vector B clearly points in the negative y direction, so I need a negative sign sitting in that y component. When you have vectors that lie along a coordinate axis, one of the components has to be 0, all the magnitude has to be in the non-zero component, and then just make sure you get the right sign. The other situation, of course, is if we have a vector that doesn't lie along a coordinate axis. Well, in that case, you're going to have two non-zero components. And so what we need to do is, again, think about three things. So for each component, we're going to think about the following things. One is, what's the sign? Do I need a positive sign or a negative sign when I think about this component? 2, what's the magnitude of the vector? And again, that's what we've been told. And then 3, I'm going to use an angle that's less than 90 degrees, and I need to make sure I use the right trig function to calculate out what that component is. So if you think about vector c here, the x component along the x-axis, the y component along here in y, pointing in the y direction, basically gives me a right triangle. So I can use my trigonometric functions, cosine and sine, to figure out what the two sides of this right triangle are, and which trig function I use, sine or cosine, is going to depend on which angle I've chosen, which angle I've picked to define for that particular vector. So as an example here with vector c, again, I'm told vector c has a magnitude of 20 meters and points 35 degrees above the x-axis. So for the x component, again, we said the first thing I'm going to do is think about sine. Well, the x component clearly points in the positive x direction. So vector c points up and to the right. The to the right is the positive x direction. So I know that the sign I want for its x component is going to be positive. The magnitude of this vector is 20 meters. And then the trig function, well, since I have my 35-degree angle defined relative to the x-axis, that means this x component is defining the adjacent side of that right triangle, and so the x component needs to get the cosine. So the way that I'm going to tend to frame this, just because it's a nice heuristic, it's easy to remember, and you get comfortable with it pretty quickly, is whichever axis we've drawn that angle into. So you either drew it into the x-axis or you drew it into the y. Whichever axis you drew that angle into, that component needs the cosine function. So to calculate out the x component for vector c, I know it's going to be positive, magnitude of 20 meters, times, in this case we said we needed the cosine of 35 degrees because that 35-degree angle is defined relative to the x-axis. Plug all that into my calculator, and so that I get the x component of vector c is 16.4 meters. I need to play the same game for the y component. And again, we said that vector c points up and to the right, and so the up is in the positive y direction. That means I need a positive sign for the y component. Magnitude's the same. So one of the things you always want to do to check is the magnitude should be plugged in the same for both your x and y components. And then in this case, again, because we said that 35-degree angle is relative to the x-axis, the cosine 35 is going to go with the x component, which means the sine 35 is going to go with the y. So when I calculate out the y component of vector c, positive 20 meters times the sine of 35, plug all that into my calculator, and I get plus 11.5 meters. So this means that vector c has an x component of 16.4 meters and a y component of positive 11.5 meters, which is another way of saying vector c points 16.4 meters in the positive x direction and 11.5 meters in the positive y. Another way of telling you what vector c is by telling you how much you need to go in the x direction, then how much you need to go in the y direction. I've clearly communicated to you what vector c is. Let's look at another example quickly. So here I've got vector d, but notice I'm told its magnitude of 10 meters, but I'm also told that it points in the direction 245 degrees from the x-axis. And we said that in doing this, we want angles that are less than 90 degrees. So the first thing that I'm going to do is say, well, if that's 245 degrees from positive x all the way around to vector d, well, it's 180 from positive x to negative x, which leaves me 65 more degrees to go from the negative x-axis to what vector d is. So this must be a 65-degree angle, but it's a 65-degree angle that vector d makes with the x-axis. I'm going to need that information. So again, thinking about the x component, my three things, I need to think about sine. In this case, vector d points down and to the left. That to the left means that its x component is negative. Magnitude we were told was 10 meters. And then because I have my 65-degree angle relative to the x-axis, the x component will get the cosine of 65 degrees. So I calculate out that the x component of vector d is negative 10 times the cosine of 65 degrees, which is negative 4.2 meters. Play the same game for the y component. Again, we said the vector points down, so that's going to be a negative y component. Magnitude still 10 meters. And again, because our 65-degree angle is defined relative to the x-axis, cosine 65 went with the x component, which means sine 65 needs to go with the y. So to calculate out the y component of vector d, it's negative 10 times the sine of 65, which is negative 9.1 meters. So again, I can report vector d has an x component of negative 4.2 meters and a y component of negative 9.1 meters, which again means that it points 4.2 meters in the negative x direction and 9.1 meters in the negative y. Now, just to emphasize the point, we didn't have to choose the particular angle that we did. So instead of picking the 65-degree angle that vector d makes with the x-axis, we could have picked the 25-degree angle that it makes with the y. And so again, now that I've defined this angle relative to the y-axis, I need to pay attention to that information when I'm picking the trig functions for my components. So for my x component, again, it's still going to be negative, still a magnitude of 10 meters, but now because that's a 25-degree angle defined relative to the y-axis, the y component's going to get cosine of 25 degrees, which means the x component's going to get the sine. For the y component, still negative because it points down, still a magnitude of 10 meters, but now that 25-degree angle is relative to the y-axis, so the y component gets cosine 25. So I can calculate out using my different angle, but notice I get the same answers. So the x component is now negative 10 times the sine of 25 degrees, but that's still negative 4.2 meters, same as it was before. The y component, negative 10 cosine 25 degrees, still negative 9.1 meters. The important detail is not which angle you pick, as long as you get the right trig function with whichever angle you choose to use. So pay attention to, once you pick an angle, which axis have you drawn that angle into? Is it drawn into the x or the y? Knowing which axis you've drawn the angle into is going to let you figure out where your cosine and sine functions need to go.